Welcome everyone. Today, we're going to dive into an essential concept in chemistry and physics, the ideal gas law. This law connects pressure, volume, temperature, and the number of moles of gas. Understanding how these variables interact with each other helps us explain a variety of real-world phenomena, from the behavior of gases in a laboratory to processes in aerospace and medicine. Let's explore how the ideal gas law works and why it's so useful.
What is the ideal gas law? The ideal gas law is a fundamental equation that describes the state of an ideal gas. It's one of the key principles that ties together several gas laws like Boyle's law, Charles' law, and Avogadro's law. These individual laws each describe a specific aspect of how gases behave, like how pressure changes with volume or how volume changes with temperature. But the ideal gas law combines all of these into one equation that covers all the basic behaviors of gases. The equation itself is PV is equal to nRT, where P stands for pressure, which is the force exerted by gas molecules on the walls of their container. It's measured in atmospheres or atm or pascals PA. V is volume, the amount of space the gas occupies, often measured in liters or cubic meters. N represents the number of moles of gas, essentially the quantity of gas particles. R is the gas constant, a universal value that ties together the units in the equation. It's typically 0.0821 liters per atmosphere per mole per Kelvin when used in gas calculation involving atmospheres and liters. T is temperature, which must always be measured in Kelvin, the absolute temperature scale. The ideal gas law allows us to predict and calculate how gases will behave under different conditions. It is essentially useful because it relates macroscopic quantities like pressure and volume to the amount of gas and its temperature. This equation is widely applied in scientific fields and industries like medicine, engineering, and environmental science.
Now, let's take a closer look at each of these variables. Understanding each of them is the key to using the ideal gas law effectively. First, pressure, or P. Pressure is the force exerted by a gas molecule as they collide with the walls of their container. Think of it like a balloon filled with air. The gas molecules inside are constantly moving and colliding with the rubber walls. The more frequently and the forcefully they collide, the higher the pressure. In the ideal gas law, pressure is typically measured in atmosphere or atm, but it can also be in pascals or PA, or other units depending on the context. Next is volume, or V. Volume is the space occupied by the gas. It's often measured in liters, but it can also be in cubic meters or other units. The volume is important because, according to Boyle's law, as pressure increases, the volume tends to decrease, assuming temperature is constant. Similarly, increasing the temperature of a gas increases its volume if pressure remains constant. Next is temperature, or T. Temperature is a measure of the kinetic energy of the gas molecules. The higher the temperature, the faster the molecules move. In the ideal gas law, temperature must be measured in Kelvin. Why? Because absolute zero, where molecular motion ceases, is 0 Kelvin. This makes the Kelvin scale ideal for gas law calculation. Next is mole, or N. Moles are the amount of substance present. 1 mole of a substance is equivalent to 6.022 times 10 to the power of 23 molecules, which is known as Avogadro's number. The more moles of gas you have, the greater the volume or pressure, depending on the other conditions. Next is gas constant, or R. R is the constant that links the other variables. The value of R depends on the unit used, pressure, volume, and temperature. For instance, when working with atmospheres, liters, moles, and Kelvin, R equals 0.0821 liters times atmospheres per mole times Kelvin. Now that we know what each variable means, let's understand how they interact with each other in the next slide.
The ideal gas law came from a combination of several earlier gas laws, each describing one aspect of gas behavior. The first one is Boyle's law. It says that pressure and volume are inversely related when temperature is constant. If the pressure goes up, the volume decreases and vice versa. The second one is Charles' law. It shows that volume and temperature are directly related when pressure is constant. If the temperature increases, so does the volume. Then the last one is Avogadro's law. Tells us that the volume of gas is directly proportional to the number of moles, assuming temperature and pressure are constant. By combining these laws, we arrive at the ideal gas law, which gives us a more complete picture. This equation also allows us to rearrange it to solve for any variable if the others are known. For instance, to find moles, rearrange the equation to N PV over RT. To find volume, use V equals nRTP over V. To find pressure, use P equals nRT over V. The ideal gas law makes several assumptions about gases. The gas molecules are point particles, meaning they don't have volume themselves. There are no intermolecular forces between the molecules. It holds true mostly at high temperatures and low pressures, where gases behave more ideally. At extreme conditions like low temperature or very high pressures, real gas deviate from this ideal behavior, which is why we use modified equations like the van der Waals equation. To conclude, the ideal gas law is
While the ideal gas law is incredibly useful, it does have limitations. It assumes that gases behave perfectly, but real gases don't always follow this behavior, especially under extreme conditions. High pressure and low temperature. At high pressure, gas molecules are closer together, and the assumption that they are point particles no longer holds true. Additionally, at low temperatures, molecules move slower, and intermolecular forces become more significant. Real gases. In these cases, the van der Waals equation is used instead, which accounts for both the volume of gas molecules and intermolecular forces. For example, when gases are cooled to the point of liquefaction, the ideal gas law fails because it cannot account for the forces between gas molecules that cause them to condense into liquids.
The ideal gas law is used in a wide range of practical applications, from aerospace engineering to environmental science. Here are some examples. First, the aerospace. The ideal gas law helps engineers calculate the gas pressure and volume in spacecraft and aircraft cabins, which need to maintain a certain pressure to ensure the safety of passengers and crew. Second is medicine. In medicine, the ideal gas law is used to understand the behavior of gases in anesthesia delivery systems and respiratory devices. For instance, it helps in determining the correct volume of oxygen needed for a patient under different conditions. Last is environmental science. The ideal gas law also plays a role in studying atmospheric gases. Scientists use it to measure and predict the behavior of gases in the atmosphere, which is important for understanding pollution and climate change. Let's take a quick example calculation to see how we can use the ideal gas law in practice.
Let's calculate the volume of gas in a situation where we know the number of moles, pressure, and temperature. For example, what is the volume of 2 moles of gas at 1 atmosphere and 273 Kelvin? We can use the ideal gas law equation. V is equal to nRT over P. Now, we want to solve for V, the volume. We can arrange the equation to get V is equal to nRT over P. This formula will help us calculate the volume when we know the values for N, R, T, and P. Substitute the known values. We know N is equal to 2 moles, the amount of gas. R is equal to 0.0821 liters times atmosphere over mole times Kelvin, the gas constant. T is equal to 273 Kelvin, the temperature in Kelvin. P is equal to 1 atmosphere, the pressure. So, let's substitute these values into the equation. V is equal to 2 times 0.0821 times 273 over 1. Now, let's calculate it step by step. First, multiply 2 moles by the gas constant 0.0821 liters times atmosphere over mole times Kelvin. 2 times 0.0821 is equal to 0.164 liters. Next, multiply by the temperature in Kelvin 273 K. 0.1642 times 273 is equal to 44.8 liters. Finally, divide by the pressure, which is 1 atmosphere. 44.8 liters over 1 is equal to 44.8 liters.
To conclude, the ideal gas law is a crucial tool for understanding how gases behave under standard conditions. It's widely used in various fields, from chemistry to aerospace, and it helps us to make predictions about gas behavior. However, remember that it assumes ideal conditions, and for extreme cases, real gas laws like the van der Waals equation are more accurate. So, while the ideal gas law is a great first step, it's important to consider more advanced models when conditions deviate from the ideal. Thank you for joining me in exploring the ideal gas law. I hope this discussion have given you a deeper understanding of how gases behave and why this law is so crucial in the scientific field.